Electromagnetic waves. Light. This question has been asked by many humans for centuries, but there was no answer until electricity and magnetism were unified into electromagnetism, as described by Maxwell's equations. These equations show that a time-varying magnetic field acts as a source of electric field, and that a time-varying electric field acts as a source of magnetic field. These E and B fields can sustain each other, forming an electromagnetic wave that propagates through space. Visible light emitted by the glowing filament of a light bulb is one example of an electromagnetic wave. Other kinds of electromagnetic waves are produced by Wi-Fi base stations, X-ray machines, and radioactive nuclei. In this chapter, we'll use Maxwell's equations as the theoretical basis for understanding electromagnetic waves. We'll find that these waves carry both energy and momentum. In sinusoidal electromagnetic waves, the E vector and B vector fields are sinusoidal functions of time and position, with a definite frequency and wavelength. Visible light, radio, X-rays, and other types of electromagnetic waves differ only in their frequency and wavelength. Our study of optics in the following chapters will be based in part on the electromagnetic nature of light. Unlike waves on a string or sound waves in a fluid, electromagnetic waves do not require a material medium. In the light that you see coming from the stars at night has traveled without difficulty across tens of thousands of hundreds of light years of nearly empty space. Nonetheless, electromagnetic waves and mechanical waves have much in common and are described in much the same language. Before reading further in this chapter, you should review the properties of mechanical waves as discussed in chapter 15 and 16. Maxwell's equations and electromagnetic waves. So you should review the properties of mechanical waves as discussed in chapter 15 and 16. In the last several chapters we studied various aspects of electric and magnetic fields. We learned that when the fields don't vary with time, such as an electric field produced by charges at rest or the magnetic field of a steady current, we can analyze the electric and magnetic fields independently without considering interactions between them. But when the fields vary with time, they are no longer independent. Faraday's law tells us that a time-varying magnetic field acts as a source of electric field, as shown by induced EMFs in inductors and transformers. Ampere's law, including the displacement current discovered by James Clerk Maxwell, shows that a time-varying electric field acts as a source of magnetic field. This mutual interaction between two fields is summarized in Maxwell's equations presented in section 29.7. Thus, when either an electric or a magnetic field is changing with time, a field of the other kind is induced in adjacent regions of space. We are led, as Maxwell was, to consider the possibility of an electromagnetic disturbance, consisting of time-varying electric and magnetic fields that can propagate through space from one region to another, even when there is no matter in the intervening region. Such a disturbance, if it exists, will have the properties of a wave, and an appropriate term is electromagnetic wave. Such waves do exist. Radio and television transmission, light, X-rays, and many other kinds of radiation are examples of electromagnetic waves. Our goal in this chapter is to see how much waves are explained by the principles of electromagnetism that we have studied thus far, and to examine the properties of these waves. Seven. Should have started with this one, probably. How many pages is this? 300 pages. Electricity, magnetism, and light. The theoretical understanding of electromagnetic waves actually evolved from a considerably more devious path than the one just outlined. In the early days of electromagnetic theory, the early 19th century, two different units of electric charge were used. One for electrostatics and the other one for magnetic phenomena involving currents. In the system of units used at that time, these two units of charge had different physical dimensions. Their ratio had units of velocity, and measurements showed that the ratio had a numerical value that was precisely equal to the speed of light. At the time, physicists regarded this as an extraordinary coincidence and had no idea how to explain it. In searching to understand this result, Maxwell proved in 1865 that an electromagnetic disturbance should propagate in free space with a speed equal to that of light, and hence the light waves were likely to be electromagnetic in nature. The disturbance should propagate in free space with the speed of light. At the same time, he discovered that the basic principles of electromagnetism can be expressed in terms of the four equations that we now call Maxwell's equations, which we discussed in section 29.7. These four equations are Gauss' law for electric fields, Gauss' law for magnetic fields, showing the absence of magnetic monopoles, Faraday's law, and Ampere's law. Including displacement current. These equations apply to electric and magnetic fields in vacuum. If a material is present, the electric constant epsilon naught and magnetic constant mu naught are replaced by the permittivity epsilon and permeability mu of the material. If the values of epsilon and mu are different at different points in the regions of integration, then epsilon and mu have to be transferred to the left sides of equations. 29.18, 29.21 respectively, and placed inside the integrals. The epsilon in equation 29.21 has also has to be included in the integral that gives d phi over dt. Okay. I have no much of clue what the hell. According to Maxwell's equations, a point charge at rest produces a static electric field but no magnetic field, whereas a point charge moving with a constant velocity produces both electromagnetic field. Maxwell's equations can also be used to show that in order to a point charge to produce electromagnetic waves, the charge must accelerate. In fact, in every situation where electromagnetic energy is radiated, the source is accelerated charges. Generating electromagnetic radiation. Every mobile phone emits signals in the form of electromagnetic waves. that are made by accelerating charges. Power lines carry a strong alternating current, which means that a substantial amount of charge is accelerating back and forth and generating electromagnetic waves. These waves can produce a buzzing sound from your car radio, but you drive near when you drive near the lines, generating electromagnetic radiation. One way in which a point charge can be made to emit electromagnetic waves is by making it oscillate in simple harmonic motion, so that it has an acceleration at almost every instant. The exception is when the charge is passing through its equilibrium position. Figure 32.3 shows some of the electric field lines produced by such an oscillation point charge. Field lines are not material objects, but you may nonetheless find it helpful to think of them as behaving somewhat like strings that extend from the point charge off to infinity. Oscillating the charge up and down makes waves that propagate outward from the charge along these strings. Note that the charge does not emit waves equally in all directions. The waves are strongest at 90 degrees to the axis of motion of the charge, while there are no waves along this axis. The waves are strongest at 90 degrees to the axis of motion, and there are no waves along this axis. And this is sort of 90 degrees, but it's not like a straight line. This is just what the string picture would lead you to conclude. There is also a magnetic disturbance that spreads outward from the charge. This is not shown. Because the electric and magnetic disturbances spread or radiate away from the source, the name electromagnetic radiation is used interchangeably with the phrase electromagnetic waves. Electromagnetic waves with macroscopic wavelength were first produced in the laboratory in 1887 by the German physicist Heinrich Hertz, from whom the SI unit frequency is named. As a source of waves, he used charges oscillating in LC circuits. For LC circuits, see section 30.5. Oh yeah. LC circuit is in fact a capacitor circuit with circuit containing an inductor and a capacitor show an entirely new mode of behavior characterized by oscillating current and charge. This in sharp contrast to the exponential approach to a steady state situation that we have seen with both RC and the RL circuits. In the LC circuits, we charge the capacitor to a potential Vm, an initial charge Qm on its left hand plate, and then close the switch. What happens? The capacitor begins to discharge through the inductor. Because of the induced EMF in the conductor, the current cannot change instantaneously. It starts at 0 and eventually builds up to a maximum value Im. During this build-up, the capacitor is discharging. At each instant, the capacitor potential equals the induced EMF, so as the capacitor discharges, the rate of change of current decreases. When the capacitor potential becomes 0, the induced EMF is also 0 and the current has leveled off at its maximum value Im. Capacitor fully charged, 0 current, circuit energy all stored in electric field. In an oscillating LC circuit, the charge on the capacitor and the current through the inductor both vary sinusoidally with time. Energy is transferred between magnetic energy in the conductor UB and the electrical energy in the capacitor UE. As in simple harmonic motion, the total energy E remains constant. All energy stored in an electric field. Capacitor discharging I increases. Capacity fully discharged, current maximal. Circuits energy all stored in magnetic field. This is an inductor, just a coil. Capacitor fully charged. Circuit's energy all stored in electric field, magnetic field. Okay, this makes sense. As a source of waves, he used charges oscillating in LC circuit. He detected the resultant electromagnetic waves with other circuits tuned to the same frequency. Resulting electromagnetic waves. He detected the resulting electromagnetic waves. Hertz also produced electromagnetic standing waves and measured the distance between adjacent nodes, 1/2 wavelength, to determine the wavelength. Knowing the resultant frequency of his circuit, he then found the speed of the waves from the wavelength frequency. Relationship. He established that their speed was the same as that of light. This verified Maxwell's theoretical prediction directly. Motion seen at 5 instants during oscillation period T. The charge trajectory is in the plane of the drawings. At t equals 0, the point charge is at its maximum upward displacement. The arrow shows one kink in the lines of electric field as it propagates outward from the point charge. The magnetic field not shown contains circles that lie in planes perpendicular to these figures and concentric with the axis of oscillation. So like lines like these. The modern value of speed of light is this. Recall from the section that this value is the basis of our standard of length. 1 meter is defined to be the distance that light travels in. This is distance. This is second. For our purpose, this is distance, this is speed. Gives you time. For our purposes, is sufficiently accurate. In the wake of Hertz's discovery, Guglielmo Marconi and others made radio communication a familiar household experience. In a radio transmitter, electric charges are made to oscillate along the length of the conducting antenna, producing oscillating field disturbances like those shown in this figure. Since many charges oscillate together in the antenna, the disturbances are much stronger than those of a single oscillating charge and can be detected at a much greater distance. In a radio receiver, the antenna is also a conductor. The field of the wave emanating from a distant transmitter exerts forces on free charges within the receiver antenna, producing an oscillating current that is detected and amplified by the receiver circuitry. For the remainder of this chapter, our concern will be with the electromagnetic waves themselves, not the rather complex problem of how they are produced.